Hello, Ekoparty, and welcome to reverse engineering a real estate lockbox or exploitation of a hardened MSP430 device. My name is Braden Thomas. Sorry, 1 second here. Okay. This is not ideal, but it'll work. Okay. My name is Braden Thomas, and as mentioned, I'm a senior research scientist at Accuvant, where primarily I focus on embedded devices, reverse engineering, and exploit development. Previously, I worked at Apple Product Security, and as a result, I have a software perspective. So if you're a software guy like me, and you see this is a hardware talk, don't be scared off because I approach hardware problems from a software guy's perspective. So today we're going to talk about this lockbox right here, and I'll describe what it is and how I reverse engineered the Android app that accompanies it, how you open the device and perform firmware extraction, what techniques I used and what techniques I tried to use and failed. And then I'll talk about findings and I'll show you a couple of demos. But before we get into that, let's talk about why it's interesting. So with Kickstarter and Internet of Things, you're seeing a large number of embedded devices enter the marketplace. And generally, they're developed kind of on a shoestring budget. You want to get your device out quickly and cheaply. But at the same time, there's this increased scrutiny on security. So these manufacturers are incorporating cryptographic protocols into their devices. And they're generally doing this by storing cryptographic secrets on their microcontrollers and relying on security features of those microcontrollers to prevent them from being extracted, which is cheap and it's really easy. But it's not necessarily smart, and I think this lockbox is a case study of why that is. Finally, it's interesting because you can hack into houses over Bluetooth, and that's just inherently cool. So the lockbox in question is produced by an unnamed manufacturer. These issues are not addressed yet in the wild, so I'm not going to name the manufacturer. And what it is, it's a real estate physical key container. So when you want to sell a house in most of the major urban markets in the US, you put your keys inside this lockbox, and if a realtor wants to show your house, they come along, they pull out their smartphone, and they can drop your keys right out of the box and go into your house. It's this particular lockbox is the #1 in the market. There's one other competitor that has decent market share, and that's called Centralock. This particular manufacturer produces 3 lockboxes. There's the original lockbox, which is based off of IR. Then there's a more recent one, which is based off of legacy Bluetooth. And then the very most recent one that came out just this past year is based on Bluetooth LE, so you can speak to it just natively with an iPhone. To actually open a lockbox, you're going to need a key. The legacy key uses an embedded cell radio, and obviously that's kind of expensive and annoying. You don't want to lose that. So generally these days, everyone uses ekey, and that's just an iOS app. It's an Android app too. Runs on your smartphone, and you can also use a dongle or a key fob. Here's an example of one that will transmit over IR. Or over legacy Bluetooth if you have an iPhone which doesn't support legacy Bluetooth. So the first thing I did was to look at the Android app because they're trivial to decompile and to reverse engineer, and to focus on the authentication algorithm because I wanted to figure out how to open these boxes. The very first thing you'll see when you open up this app is that each ekey has a serial number and a Syscode. And this Syscode is what they refer to just an integer, and it corresponds to a regional market. So for example, I'm from Atlanta, Georgia. So Atlanta, Georgia has one Syscode. Some larger regional markets like Southern California will have multiple Syscodes. When you first run the app, the serial number and Syscode are required in an obfuscated blob that you have to provide. Presumably, you get that from your MLS association, your Realtors Association. The app then uses that serial number and Syscode as a credential to speak to the manufacturer's backend web service. It's actually the only credential that's used. This web service will provide authentication cookies, and the app can then send those cookies to the lockbox to ask it to open. And those cookies are just binary blobs of data. Those will be sent over Bluetooth or IR. And then the key to their security is that the realtor has to provide a PIN code. And this is a numeric code that they configure that's associated with the serial number and Syscode of their key, and that's required to open the lock. When I reverse engineered the app, I discovered there's two auth modes. The first is deprogrammed, and it's not really used in the wild. It's used when transferring lockboxes across Syscodes. The main one that's used is programmed auth. So it's used exclusively in the field, and it's fairly complex. It involves a lot of cryptographic operations. First, you're going to send the identity cookie. Again, these are cookies you receive from the server. Then the configuration cookie. Then the obtain key message, which incorporates that PIN code you set up. Then a key auth cookie, and then finally a device open message. And if all those cookies and messages pass validation, only then will the lockbox open. So obviously, I would want to modify these cookies so that I can, generate my own fake cookies. And I quickly discovered that they contain AES max message authentication code, so that you can't just modify them. Also, the ekey sends update bytes, which change every single day. And these are also AES max, so you can't create your own. The final problem with programmed auth is that ekey will generally open only a lockbox in its own Syscode. So while I mentioned a key has a serial number and Syscode, so does every lockbox. And those Syscodes generally have to match. At this point, it's becoming pretty clear that we needed to access the actual firmware on the device to be able to hack it. There's a number of problems we've run into so far. First, I don't have a valid serial number and Syscode because I'm not a realtor. I might be able to convince a realtor who's a friend or who's not very smart to give their serial number and Syscode to me, but I'm not a very good social engineer, so I probably wouldn't be able to get their PIN as well. And also, I don't want to have to communicate with this manufacturer's server, because then they'll know that I've been up to no good, and they can track me and get me in trouble. So the next step is to actually open this device. To physically open it, and this is the oldest, the IR-based lockbox, you're going to cut off this hard plastic shell, which will leave you with just this metal here. And you remove the two screws on the top, and you're going to then need to open the key container, which is tricky because I haven't told you how to do that yet. So you'll need to either use a legitimate ekey or an exploit. Now, the Bluetooth model you have to do all that, but then you also have to cut off the shackle, which is a little dangerous. And then you have to pop a couple rivets on the back, which is extremely difficult. It takes like an hour of messing around with a screwdriver and a hammer and a saw, and I don't recommend it. When you open them up, what you're going to see, you've got the top and bottom photos of the board on the left of the original lockbox, and the top and bottom of the Bluetooth on the right. The Bluetooth LE is basically identical to the Bluetooth, except that there's a Bluetooth serial module you can see if you look closely, and that's replaced with an LE chip. Now, if you see both of these tops have a large microcontroller on them, that's the MSP. So the original lockbox, IR-based lockbox, has an MSP430 on it, which is in TI's 1 series. And the newer has an MSP430, which is in their 2 series. They both have a serial IR transceiver because they're all backwards compatible with IR. Where the Bluetooth adds an SD microelectronics Bluetooth serial module. The only other really interesting thing on the boards is an EEPROM. And the EEPROM is actually used to store the visitor log. It doesn't contain firmware or anything. Basically, whenever you authenticate to a lockbox, if you're a realtor, your contact information and your serial number and syscode of your key will be stored in that EEPROM. So the reverse engineering steps that I took to approach this lockbox were, first, I made the decision to focus on the older IR-based lockbox. And the reason I did that is, first, because the board is so much easier to obtain. You don't have to pop those rivets. Second of all, as we all here know, older software is more likely to be insecure. But fundamentally, the cryptographic material on both the oldest lockbox and the new lockbox are the same. So if I can hack the oldest one and extract the keys, I can open every lockbox, even the brand new ones. So generally, as with most embedded devices, the process was, first, map out the test pads. And I did that just using continuity testing and the TI's datasheet. Second, find debugging interfaces in the microcontroller, and then perform firmware extraction through those debugging interfaces. Now, TI, for MSP430s, TI has two debugging interfaces on them. The first one is JTAG that everyone is familiar with. JTAG on MSPs is 4-wire and 2-wire, but my target chip, the 147, only supports the 4-wire variant. As soon as you connect, you immediately find out that the JTAG security fuse is blown, prohibiting all JTAG. So that leaves you with just BSL. BSL is TI's bootstrap loader protocol. It's a serial interface, and it mainly exists just to permit read and write access to flash memory on the microcontroller. BSL is implemented with code that's stored in a special read-only region of flash. The problem you immediately run into when you're trying to speak BSL is that nearly all commands, BSL commands, are protected with a password. And cleverly, TI, for their password, use the interrupt vector table, which is inherently unique and secret. It's unique because every device with different code will inherently have different interrupt vector addresses. And it's secret because I don't know your code, so obviously I don't know your interrupt vector addresses. Now, there's only one command that you can perform in BSL without that password, and that's mass erase. And the mass erase will erase all of flash. In addition, it'll set the interrupt vector table back to the default, which is all Fs. And you can access the chip again, but you've erased flash, so it no longer has any of the code you wanted on it. In 2008, Travis Goodspeed released a white paper called Practical Attacks Against the MSP430 BSL. He described two attacks. The first one was a voltage glitching attack, and the second one was a single clock cycle timing difference in the BSL password comparison routine. So to perform firmware extraction, I set out to implement these attacks, starting with voltage glitching. I used a GoodFet22 that I had sitting around, which is, and it has a ADG1634 on it, which is an analog-controlled digital switch. So essentially, you can switch between two analog voltages just by flipping digital I/O. And I used the onboard DAC on the GoodFet, or on the MSP that's on the GoodFet, to define those two voltages. Essentially, the idea was to have a high and a low voltage and to swap between them, causing the chip to glitch. You're going to want to remove the chip from the board to perform this kind of glitching attack because any other electrical components on the board, like capacitors, resistors, will affect the attack. Step down power on all lines. The MSP runs on tremendously low power. Famously, it can run on a grape. So you want to step down power on all those lines using resistors. I should mention that this attack is only feasible at all on BSL 1.x because in 2.x they added a feature to do a mass erase on a single incorrect password. Obviously, if you're going to be glitching, you're going to need to do a number of attempts. So when you hit the first attempt failed, it would erase the entire chip. But that wasn't a problem for me because the 147 was running BSL 1.1. When I attempted to perform this, the attack was actually a failure. I failed to reproduce the issue. The device either continued running undeterred when I glitched it, or it died altogether and stopped responding. My theory about why this was is that the MSP430 on a good FET is too slow to glitch another MSP430. A BSL runs at around 1 megahertz, and the good FET could be clocked up to 16 megahertz, but I think it's still too slow. I'd love to try this with like a chip whisper. So I moved on to the timing attack. What Travis discovered was that the password byte comparison routine had a single clock cycle timing difference between the correct and incorrect paths. And essentially, his strategy was to send every single byte, so 000, and the password's 32 bytes, all the way up to 32 FFs, and then measure the number of clock cycles that it takes to perform that password comparison. And essentially, that way you can determine the byte makeup of the password. Like it has 101, it has 2 03s, etc. He checked a few BSLs. He hadn't checked BSL 1.1 in his original paper, at least. So I extracted the BSL code using another chip that didn't have a password, and I reversed it. And I discovered it also has this comparison, this single clock cycle difference. Essentially, for every single byte, it receives it, it compares it to the correct byte, and if that byte is not the same, then it takes an additional clock cycle to or a value into a global flag that says, we got a bad password. So the problem with this attack is that to exploit it, you really need to think about what the serial communication looks like on the wire. And serial, so in this case, there's one start bit, there's 8 data bits, a parity bit, and then a stop bit. And BSL actually bit bangs this. So between bytes, the code will actually wait for the start bit to go low when it's receiving data. And if that waiting loop runs more than just one time, you've destroyed all prior timing information. And you can see here in the BSL code what this looks like. It says, have I received the start bit? If it hasn't, just does that again. Additionally, the device will check that the line is high after a stop bit, or there'll be an error. Let's look at that graphically because it's a little confusing. So between each one of those bytes, of those password bytes, you see that it checks that the line is high after the stop bit has occurred, and then it checks that the line is low during the start bit. And if it's not low there, it'll busy wait and destroy all timing information. So in the graph before, I showed that there's a time between these 2 bits. Or it's actually between 2 bytes, between the last bit of one byte and the first bit of the next. And I call that the inner byte timing. Now, obviously, determining the ideal inner byte timing, it sounds trivial. It's just take the number of instructions that are running there and multiply that by the clock speed. It's not that easy, because first of all, the clock speed is highly inconsistent. When BSL is running, the chip is using DCO clock, which is its software clock. You can't force it to use a crystal, because that's configured in code, and that's highly unreliable clock. And second of all, the number of instructions varies because of the timing vulnerability itself. Any mistakes that you make in getting that ideal inner byte timing will be multiplied by every single inner byte time. So 34 times in the case of a password, as there's 32 bytes and then a checksum. So let's look at what these problems look like graphically. Up above, you see the case where the inner byte timing is too large. And this is kind of how normal serial communication starts out. The inner byte timing is pretty large. And the device will wake up before the start bit. It'll see that it's not low yet, and it'll busy wait there until it goes low. So to determine the ideal, we're going to slowly decrease that inner byte time But what if we go too far? If we go too far, it'll either see that the bit is low during the stop, and that'll cause an error, or it'll wake up after the start bit and busy wait until the first data bit, and it'll think that's the start bit, and that's just a giant disaster. One other problem here. You can't determine the ideal inner byte time on a device where you don't know the password. Because if you don't know the password, you're going to get a NAC response. If your inner byte timing is incorrect, you're also going to get a NAC response. So there's really no way to determine whether you've gone too far or whether it's still, still too large. So you need to perform this attack on a same model chip with a known BSL password, find that ideal time, and then you can do it on your target chip. I used an external crystal on the GoodFet that I performed this attack with to eliminate any attacker side problems, and I slowly decreased that inner byte timing until the correct password was no longer acknowledged. I then know that I found the ideal inner byte time. I've eliminated all those busy waits, and I can reuse that on the target chip to do the timing attack. So this is what it looked like. You see I slowly am decreasing the inner byte timing, and the overall time is decreasing linearly. And that's because we're removing busy waits. So obviously, every millisecond or nanosecond that you decrease will result in one less clock cycle as well. So this looks really great, from a high level. But at the micro level, it was wildly inconsistent. The overall amount of time that I saw actually varied by thousands of attacker clock cycles, which is just a massive, massive difference. I tried modifying BSL itself to expose the time at which the device is reading a bit by twiddling a line. And that worked pretty well to confirm sort of my knowledge of how this inner byte time thing worked. And what I noticed was that the time between those reads was quite inconsistent between runs. So I thought it was still due to DCO clock, and I decided to focus on just the very last byte of the password. If I could get that last byte right, I would be happy, and then I could move on from there to the other bytes. Then you only need to get those 3 inner byte times correct, which, so any errors will only be multiplied by 3, just that last byte and the checksum. This was my result. I found the ideal inner byte time, and I ran each possible byte, 0 through 256 on the x-axis, 10,000 times, and then graphed the overall runtime. Now, what you would expect to see in this graph is that every single byte would be a flat line. There would all be identical number of clock cycles, except for one byte, the correct last password byte, which would be 1 clock cycle difference. And instead, this is what I wound up with. Obviously, this attack was a failure. I believe it was a failure due to inconsistencies with the DCO clock, that software clock, during the tear routine. And the tear routine is how the microcontroller determines timing for the serial communication. Essentially, it measures the number of clock cycles that it sees during the first bit that it ever receives in serial. And so if there's inconsistencies there, those would be multiplied for every single bit in the serial communication. And those don't appear to average out in the short term. So at this point, I was quite depressed. I had tried the 2 public attacks, and they were both a failure. Fortunately, there was a third attack. And this attack I call the paparazzi attack. It's a firmware extraction technique that Travis Goodspeed told me about that permits bypassing the JTAG security fuse with digital camera. And it's due to the photoelectric effect. So to review JTAG security, the 1, 2, and 4 series of MSPs use a physical fuse. And once this is blown, or programmed as they call it, it's permanently blown, whereas the 5 and 6 series use an electronic fuse, which is just programmed by writing to 17FC, can be unprogrammed by erasing it. And this technique does not work against those devices. Now, the 1, 2, and 4 physical fuse devices, the fuse check is performed by toggling the TMS line, which is one of the JTAG lines, twice, while that TDI line is kept high. And the chip will measure current that's passing in from TDI across the physical fuse, and it will remember the result if current was seen or not. The paparazzi attack requires decapping the target chip while ensuring that the bonding wires remain intact. And I just outsourced this to a lab. It costs less than $100, so it's a good deal. You might have to do jet etching if you're doing this yourself. Once you've decapped the chip, you're going to run a tight JTAG loop on the reset, tap, and fuse check operations, that toggling of TMS while keeping TDI high. And every 200 iterations, you want to attempt an authenticated action, by which I mean an action that requires the existence of the unblown fuse. And so what I just do is I read the first address in BSL memory space, which is at address C00. And that contains an entry, that word contains a pointer to the entry point of BSL, which is at C02. So if you read C00 and see C02, you've succeeded. While you're doing this, you want to expose the die and hit it with a camera flash. This requires a few attempts. If you see valid data, if you see that C02, you've succeeded. When you've succeeded, don't power the chip down or flip the reset line, which probably requires a GoodFET software modification since the GoodFET likes to reset the chip. Be sure to power the chip externally during this attack because it tends to use a lot of current. And don't expect it to be in a normal state after this. I usually just read the BSL password and move on, reset the chip, speak BSL. So why does this work? I mentioned the JTAG fuse check works by measuring current that's passing across the fuse. Now, the photoelectric effect is an effect whereby transistors, when struck with electrons, or struck with photons rather, will release electrons. And I believe that this causes the fuse check machinery on the die to believe that current has in fact passed across the that physical fuse by flipping logic gates, when in fact it hasn't. So now I'm going to show a live demo, and so hopefully this will work. Good. All right, so at this point, I told the GoodFET, which is sitting here connected to my computer, to initiate JTAG with the decap chip, which is sitting in a socket, as you saw in the photo, and it got the JTAG ID, so that means that JTAG was successful. Let's start this over. Okay, so it read a specific register, and when you see 555 from that register, you know that the JTAG fuse is blown. And at that point, any other JTAG operation would fail. So when I hit enter, it'll do that reset tap operation, that tight loop I talked about, and I'll hit it with the camera flash. And it's going to take a few times, so cross your fingers for me. I've never actually performed this outside, so this is going to require special luck as well. I'm now flashing the chip, and it's attempting to, we're attempting to bypass that fuse. OK, it succeeded. So as you can see, that required a lot of flashes, and it probably has something to do with being outside. I'm not sure. But anyway, we got the BSL password. At this point, we can initiate BSL and communicate with the chip, extract the firmware via BSL. Let's talk about findings. So what did I see when I actually reviewed the firmware? First, calling convention. So MSP430, the code that I saw, passes arg1 and R12, arg2 and R14, and any remaining arguments are pushed to the stack. Return values are in R12. Remember, this is a 16-bit processor. So R13 will also be used if it's a 32-bit return. The only really unique thing about actually reversing MSP430 assembly is the way it does a switch statement with a sparse index, non-contiguous index, where it actually calls a common helper function, which will read the return address off the stack and then parse this structure. So if you're using IDA, you're going to need to manually set up this structure because IDA will think it's code. Another interesting thing I found in the firmware, which surprised me, was that 25%, about roughly, was dedicated to IRDA. And the chip actually bit bangs it, and it's serial-ish. And when I say that, I mean it's like serial, except the pulse width is much shorter than the bit width. So you can write a custom logic plugin that'll successfully sniff this off a test pad on the board. And you can export that, and if you post-process it a little, you can actually open it up with Wireshark, which will decode most of the IRDA. It's very useful. So what did I find in the firmware? I found 4 things. First, how that crypto that I saw really works. Second, I discovered there's actually 3 authentication modes. I found a hardware backdoor. And finally, I found that the memory read and write command over IR that I had seen actually permits reading and writing flash using a hidden mode. So let's dig into those. The crypto architecture, I discovered there's actually 2 keys that all the crypto is derived from. There's a device key that's not really used much in the field, but when you do use it, you can get a high level of authentication to deprogram a device. And then there's the Syscode key. This is the root of trust for all your normal operations, like opening the key container. And it's shared by the entire geographical region, that whole Syscode. So if I were able to get this, I could open all the lockboxes in Atlanta or wherever. Cleverly, neither of these are ever accessible to the app, and they're not readable by any remote commands. So they did well. The Syscode key is programmed by some unknown process at your MLS office when the device is deprogrammed. I don't know how they get it, but they must have some authenticated channel. From it, they derived a MAC key and an encryption key. And they used the MAC key to validate those cookies, and then they used an encryption key to decrypt any other ephemeral keys. And as I mentioned, if you compromise this key, you can generate your own fake authentication cookies and open any lock in that region. I also mentioned there's a 3rd authentication mode, and interestingly, this authentication mode only permits access to the visitor log in the EEPROM, which is only useful if the device has been unlocked, because otherwise no one would be in the visitor log. The important thing is it requires no authentication cookies for access. You can just walk up and say, give me the visitor log. And from there, you get the serial number and syscode of any ekeys that have connected to it. And previously, we said I'm not a realtor, so I don't have one. This solves that problem. But we still don't have the PIN code that belongs to those. So let's talk about brute force. A PIN is only 4 digits. The device does have PIN brute force protection, which would take a full week to brute force the PIN if you wait for the lockouts. But the lockout counter is stored in the EEPROM. So if you have physical access to a device, you can erase it between attempts, and you can effectively clone an ekey, because you now have the serial number, you have the syscode, and you have the PIN code that you brute forced. Next, I mentioned there's the hardware backdoor. And I talked about deprogrammed auth before, but this is actually device key auth. If you know the device key, you can still do this kind of auth. It's the highest access mode that permits overriding keys, Likely it's used by the MLS office. They must have some secure channel to get those, I'm not sure. But the implementation of this contains the hardware backdoor. And what this looks like in firmware, if you ever see this in firmware, you know something suspicious is going on. Peripheral 3.1 goes high. Immediately after that, they test if peripheral 3.2 is high. And if it's not high, if those values are not the same, then the backdoor mode is in effect. And that's because those peripherals are connected via a resistor to each other. If you desolder that resistor off the board, you can bypass that authentication and get the highest level of access. Or you can destroy it with a drill hole in the back of a closed lockbox, affecting no other electronic components on the board, but just bypassing all of auth. So at this point, we have the ability, if you have a device in front of you, you can drill a hole in the back and you can get that high level of auth. We have the ability to clone an ekey, but still we're going to have to talk to the manufacturer's server to get those update bytes. We don't have that Syscode key. So how do we extract that without decapping? Obviously, we can do the JTAG attack to extract it, but that's expensive, or relatively, I guess, and it takes a lot of time, and it's kind of sketchy. So I mentioned before about BSL mass erase, and the keys are stored in a segment of flash called the information memory, which is erased by BSL mass erase, so you can't get access to it. On MSPs, generally, if you're going to write to flash in your code, in your firmware, you have to erase that segment before you write to it. So I mentioned the lockbox has a memory read and write command, and generally it's only used for reading or writing to the EEPROM, which contains the visitor log. But there's that one hidden mode that allows you to write to flash, and allows you to write to just that information segment, but you're not allowed to read or write to the keys there, but you can write to other things that are stored in that same segment. And the way that's implemented is the device, when it receives one of those commands, takes that entire segment, copies it to a buffer on the stack, it then erases that flash segment, modifies the stack buffer as you request, and then writes it back to flash. The key here is that the stack is in RAM, and RAM is not erased by BSL. So here's the final attack, the ideal attack to get the Syscode key. First, we use the hardware backdoor to authenticate. And I say authenticate because we don't actually need to have any keys since we destroyed that resistor. Next, we're going to use a memory write command to the information page where the keys are stored at some unused location, during which time that page will be copied to the stack buffer, modified, and written back. Very quickly, reset the device, perform a mass erase of flash via BSL, that only command that you can perform without the password, and then you can read out RAM since it's now reset to the default password. When I implemented this, I had great success. I was able to extract the Syscode key. I wrote a special good fed application that counts the clock cycles so that it resets the device at the exact right time, puts it into BSL mode, and then sometime later you can mass erase it, read out RAM, and you've destroyed the device. But you've extracted the Syscode key, so now you can just go on a crazy spree around your city opening houses. So that attack does not demo particularly well, so I'm going to demo the hardware backdoor. This is a device that I removed the cover, and I put a single drill hole in the back here. And I'm going to speak Bluetooth to this key fob, which will translate it into IR. You can see this. It's locked. So it sent the deprogrammed auth, and sometimes it takes a while. Now the device will open. So just to kind of circle up, conclusions, solutions. We described these issues to the manufacturer in June. They were receptive, and they are working on fixes. But for other applications, other devices, I would say you should avoid storing secrets in microcontrollers' flash memory. I know Atmel makes a bunch of secure storage chips that you can actually perform cryptographic operations on them, so the keys never leave, and they're intentionally hardened against physical attacks. Some greets to some coworkers who helped me, and of course, Travis Goodspeed for his awesome prior research here. And that's it.
Good. Muchas gracias, Braden.